Thank you. Thank you. Can you guys hear me? Perfect. Well, appreciate you all making time to be here. This is a very spooky conversation. We're going to be talking about a subclass of vulnerabilities that actually touch very closely on Yarden's presentation. These are logic bugs in nature, but they relate to API abuse perpetrated by authenticated users. So let's just dig into it. So in terms of the talk agenda, we're going to be touching really briefly on definitions just to get on the same page. And then I really want this to be a very practical talk. So we're going to walk through a lot of different concrete examples of these vulnerabilities. 3 of them are examples of vulnerabilities I've come across in my research. 2 of them are very recently disclosed sets of these vulnerabilities that kind of flesh out the overall shape of how these vulnerabilities can be exploited, which are really fun and interesting. And then we're going to talk a little bit about what it looks like for these vulnerabilities to be exploited. What's at stake? Kind of what's the severity of them? And then the fun part is we're going to put on our black hats for a second, pretend like we're script kiddies, and see what the 1, 2, 3 is for trying to identify and exploit these vulnerabilities in the wild ourselves, just to get a sense of how a malicious actor might be going about this process. And then we'll talk a little bit about new challenges, especially with the introduction of new technologies like LLMs and how they're making what used to be a very manual process of identifying these bugs more programmatic. And then we'll talk really briefly about mitigations. Okay, so definitions. I know I'm talking to a SANS audience, so this is a little bit elementary, but I think it's important to emphasize. When we talk about auth, we are talking about authentication and authorization. Authentication is the process by which you verify that you are who you say you are. Authorization is the process by which you verify that you have permissions to access or perform whatever is the thing that you're attempting. What's interesting is that authentication tends to be a little bit of an easier problem to solve. It's kind of a binary yes, no. Do you have valid credentials? Do you have a valid bearer token, auth token, password, passkeys, whatever? And that's true across the product that you're interacting with. But authorization is a little bit tricky. It's more nuanced. So a specific user can be authenticated across the entire app, but they might only be authorized to access a subset of endpoints or be able to interact with those endpoints in a specific way. And so as a result, authorization can be reliant on business logic that often can be implemented incorrectly. And that's where we end up finding these vulnerabilities, where an authenticated user can actually end up being a malicious actor as well. What's interesting is when you kind of look at the OWASP top 10 API vulnerabilities, a lot of them are vulnerabilities that can be exploited well by this type of an actor. So we're going to be really focusing on 2 major classes of these vulnerabilities. The first is Broken Object Level Authorization, often referred to as BOLA. Broken Object Level Authorization is a set of vulnerabilities related to the manipulation of an API call payload to change what is a user, or sorry, an object identifier. Often it can be a user ID or some other type of ID to allow the call to access data or perform actions that it otherwise should not have permission to access. We'll talk about a couple of concrete examples of that. Broken Function Level Authorization is a very closely related class of vulnerabilities that relate to the manipulation of call payloads to allow actions to be performed by effectively access to functions that a user should not have access to. So a really good example, simple example of this is a user having access to edit or delete a record that they only should have read access to. And there are a whole host of other vulnerabilities. We'll kind of touch on a couple of these as we go along, but the first 2, BOLA and BFLA, are the primary focus of this conversation. Now, when I talk about APIs and these types of vulnerabilities, I think it's also important to mention that we're really talking primarily about front-end APIs. So today, when you go to a web app or you use a SaaS product, you're effectively interacting with a UI that's an abstraction on top of a bunch of API calls back to the product servers. So for example, if you go to the Twitter homepage, you load up your feed, your device will make something like 220 different calls to different endpoints. And in those calls, a bunch of them are, performance telemetry for the app just to track you and see where you are. But a couple of them are to endpoints that actually return real data. And hopefully this is legible to the audience here, but there's an endpoint that's actually called when you first load your timeline, if you're logged in, called home timeline. And that endpoint actually triggers a bunch of different microservices at X or Twitter to identify based on who you follow, your profile, kind of the ads that should be served to you, what are the top 20 tweets that should get pumped back into your timeline and hydrated into your timeline. And that endpoint is just a request, a network request. And it sends back a JSON response with all of the data that feeds your timeline feed. And so that endpoint is really intended to be just used by the client front end. It's not meant to be used by developers or SDK. It's not an SDK API, but it's an API and anyone can call it. So that's where you run into these challenges where APIs that are technically undocumented, they're not meant to be used in a programmatic fashion, end up being abused by more technical malicious actors. Okay, so let's talk about our very first example. This is a vulnerability found in an electronic health record system, which is a piece of software used by physicians' practices to manage all of their clinical information. So all of your patient records, your schedule, your clinical encounter data, what happened during appointments, the documentation for the notes, and also your claims information. So what you submitted as charges for these claims to insurance companies, what got paid back, what was settled. All of the data for a healthcare practice. This electronic health record system is used by something around 10,000 different physicians' practices across the US. A lot of them are primary care doctors, managing in total about 15 million patient lives. It's a really good piece of software. People like it in general. And in part, it's because it has really nice functionality built into it that makes the work of a back office manager really easy. So in this case, if you're logged in as a practice employee, you're able to go into a modal where you can look up claims related to a specific patient and click a nice little print button. That print button allows you to get a PDF output that the patient can take with them to another doctor, or you can submit on their behalf to a health system or another referring physician to effectively, that encapsulates all of their clinical history with your practice. It's all of their claims information for all the different sort of encounters they've had with your practice. That little print button ends up being the point of vulnerability, and it's really interesting. When you click that print button, it calls an endpoint that triggers a microservice. That microservice looks up the call payload that was submitted to it and looks for an ID value related to the claim that was opened on your modal. That claim ID is then looked up against the database. All the records related to that claim ID are returned back to the printer microservice. It puts it into a nice PDF template, sends it back to the client device. Now, the microservice itself nor the database have any type of authorization function that validates whether that call is supplying a claim ID that is valid for that user. And so what you end up having is the ability as an authenticated user who's logged into the service to manipulate that claim ID and return claims for unaffiliated patients. And what makes this particularly pernicious is that that claim ID is a global identifier across all practices that are on the software, and it's an incrementing integer. So it makes it very easy to guess. You start with a valid claim ID, increment up, decrement down, and very quickly you have claims related to all 15 million or so patients' lives that have ever interacted with the software. Obviously, very, very sensitive issue and a very simple problem. And what's interesting is this is an authorization flaw in just this specific printer microservice. The other endpoints for this software don't have the same vulnerability. Okay, hopefully that was not too spooky. Still have you guys. Next, we're going to talk about a broken function level authorization vulnerability. This is related to a different electronic health record system. And it too is well liked by users, in part because of its nice functionality. One of the features that it has is, as a physician, you can log in, you can go to each patient's history and look up their encounter information. You click on an encounter and you see what were the procedures that were performed that day. As a physician, you're meant to be able to delete these encounters if they were erroneous. You can edit them to add new codes, delete codes, etc. And it's a nice little pop-up modal with these two buttons at the bottom that say edit and delete. That edit and delete, when you click them, call the same endpoint with the function of edit and delete in the call payload hard-coded in. Now, what's really nice about this software is it also has a nice patient interface. Patients can log in and go to their own encounter histories and look up, and they'll see a very similar modal to what the physicians see. They'll see kind of the summary of what happened during those encounters. But in the patient UI, you actually don't have those two buttons at the bottom. The edit and delete button don't exist. But just because they don't exist doesn't mean that patients can't perform those actions. Something's not clickable does not mean something's not callable. And so if you are a sophisticated malicious actor and somehow familiar with the software, you might know that you can call the payload with these functions in your call payload and return that action, either to edit a particular encounter history or to delete it. This broken function level authorization vulnerability is also coupled with BOLA. Turns out that you can actually perform this action on other patients' encounters as well. So as a patient of a practice, you can go in and very quickly, wreak havoc, delete the history of the practice with all the other patients in a programmatic fashion. Okay, hopefully not too spooky. So we're going to talk about something a little bit less spooky, but very common, which is unmitigated resource consumption. This actually tends to be very common across web apps and particularly across these front-end APIs. Just to give you a sense of tangible sense of what this really means, if you go to a product that has an infinite scroll feed or something that requires data to be refreshed on a recurring basis as a user is interacting with a product, they tend to call an API endpoint that requires them to submit kind of a starting point, ending point, number of rows returned. That's typically a common structure used in these calls. And what you can find is that the starting point and ending point programmatically often can be changed, and the number of rows returned can be programmatically changed. You can just kind of edit those call elements and return different sizes of data effectively. A really tangible example of this is a product called Tegus. Tegus is an expert network where users can subscribe and interact with domain experts. They can schedule calls with them, have interviews with them, and transcripts of those interviews are logged in the transcript library for the entire Tegus platform. What's really nice about Tegus is if you are subscribed to it, and it costs quite a bit of money to subscribe on an annual basis, like $10,000, $20,000, something like that, you get access to the full transcript library. What that allows you to do is just go and read as many transcripts as you want, learn about all these different topics, see what other people talk to these domain experts about. The assumption in the Tegus product is that no individual is going to completely exhaust the transcript library in one go. But it turns out there's a particular interface that used to be vulnerable that would populate the latest 20 interviews that had been transcribed and logged into the library when you first logged into Tegus. And that call, that sort of modal would be populated by an endpoint call that had a hard-coded value for how many rows should be returned. And I think specifically it said the first 20 latest transcripts would be returned for that feed. You could actually edit that 20 and say 2,000. And what used to be a call that would take a second and a half would take maybe about a minute and return for you 2,000 transcripts. Now you can imagine, why stop at 2,000? Let's go to 20,000. Turns out the microservice that actually was behind this, this endpoint didn't time out within the time band that you needed to effectively exhaust the entire transcript library. So there was a case of this being exploited where effectively the entire transcript library was dumped and hosted online, ended up being taken offline. Tegus patched this, but it kind of gives you a sense of how these types of vulnerabilities can also, despite seemingly being relatively benign, be destructive. As you can imagine, if you are Tegus, your entire value proposition is the transcript library. So if someone can access it for free, why subscribe? Okay, we're gonna get back to spookier stuff. This is an example of a vulnerability found by a research firm in the UK called Fortbridge in a dating app called Field. Field is a dating app used by, I believe, in the order of hundreds of thousands of users. And Field itself is a really interesting example of what happens when you don't implement authorization at all. An interesting, idea. Effectively, what the research firm found is that when you interacted with the product, it would call a bunch of different endpoints. So for example, if you went to your own photo library on the dating app, it would call an endpoint that would take your user ID and return for you all the photos that you had uploaded into the app. So you as a user should be able to see the photos that you've uploaded into the library, obviously. You could edit your user ID and replace it with some other user's ID, and it turns out it would return for you the photos in that user's library as well. And it goes even further. It turns out when you send a message from Field to another user, it would call an endpoint that would take from user ID to user ID and the message that you were sending, and log that into the database, and it would populate in your apps. What you could actually do is edit the from and to field and effectively say from this other user ID to another user, and this is the message, and effectively start sending messages on behalf of other users in an unauthorized fashion. For a product that is intended to be extremely private, the dating apps contain a lot of sensitive information. It was totally open and completely vulnerable to all users who had a little bit of sophistication around being able to technically call these endpoints. It took Field about 6 months to patch this. So it kind of also gives you a sense of, once it's known, how difficult it can be to go back through your product and re-architect things to resolve these types of logic bugs. Okay, and our final concrete example, this is maybe my favorite. This was disclosed in the past few weeks and patched within 24 hours, but it's a really interesting example of an authorization vulnerability that leads to remote code execution, which is mind-blowing to me. It was found within a product called Arc. Arc is a modern web browser that was built by a startup called The Browser Company. Arc is built with the intention to kind of create new user formats for people who are on the internet. So it's supposed to change your experience with the internet. And part of the way they do that is through a feature called boosts. Boosts are effectively custom scripts that you can upload into your Arc profile that allow you to change the way the internet looks for you or performs for you. So you can change typefaces, you can change the colors, you can turn every website into grayscale if you want. And it's effectively just scripts that will run in the background of your browser and interact with whatever website you're on. So a simple example might be you might have a script running that every time you go to the New York Times homepage and you highlight a piece of text, maybe it takes that piece of text and forwards it into a database that logs all of the quotes that you want to log. It's kind of a nice feature. It's a nice idea. The way boosts were implemented is these scripts were logged in a Firebase database, and the scripts are intended to be used across all of your Arc experiences. So you can have Arc on your mobile app, you can be interacting with Arc on your laptop, and as long as you're logged into the Arc browser, your profile is supposed to have all the scripts accessible across all of your devices. It turns out that you could actually upload and edit boosts on behalf of other users without having to go through an authorization step. And so you can imagine you can upload a script, change the user ID that's supposed to be yours in the call payload, and replace it with another user's ID, and suddenly upload scripts that they never intended or know about even into their Arc profile. And very quickly, you can end up with something that, in the worst case scenario, could be a keylogger tracking every Arc user's experience with Arc. Very cool, very interesting version of this vulnerability, patched very quickly. And I believe as of a few days ago, the browser company announced that they're no longer working on Arc, they're pivoting to a new product. I don't believe it was related to this vulnerability, but it also, for the, I believe, like million or so active users they have, a little bit of a sad ending. Okay, so let's talk about spectrum of severity. We talked a lot about how scary and vulnerable companies can be or products can be to these types of vulnerabilities, but it's a broad range. What's actually interesting is when finding these vulnerabilities and reporting them, you find that a lot of product owners are actually aware that individuals are programmatically interacting with their front-end APIs, and they're kind of ignoring it. In some cases, they see it as a net benefit. It's effectively like having an SDK that you never had to document, you never had to manage or build for other developers who want to integrate with your product. And that kind of sort of like shadow API is outside of terms of service. So at any point, if you decide someone's integrated with your product in a way that you don't like, you can just shut them off very quickly and potentially seek damages. So there are a lot of teams who are aware that people are interacting with their APIs this way, but kind of ignoring it. And then you kind of get into the other end of the spectrum where it actually is harmful and perceived to be harmful by product owners. The truth is, a lot of the time, these authorization vulnerabilities don't fall within the category of urgent. They might be considered high priority. So for example, in the context of Field, obviously, if that leak was made public, it would destroy the company, and you would consider it to be immediately urgent. but it can take time for teams to come around to recognizing those vulnerabilities and actually acting on them. What's tough, though, is that a lot of these vulnerabilities are actually shifting increasingly to the right end of that scale, so being perceived to be more and more vulnerable. And part of that is because a lot of modern web app frameworks, by default, create accessibility for the backend. So a really simple example of this is a really good tweet on the left-hand side that highlights that if you're building a Next.js app and you use the use server config as your default, that will actually create API endpoints, public-facing API endpoints for all exported functions, even exported functions that are not actually used within your client. So what that means is a backend developer might be building something thinking that it's a pure function, it's internal-facing, but because of this config, they have an unknown public endpoint available and accessible for others to call. Similarly, on the right-hand side is an example of how users are becoming more sophisticated and kind of getting around UIs as a limit for how they can interact with your product. So Theo is a developer, is a Twitter celebrity, kind of a fun Twitter account. But he kind of wrote this tweet that I thought was really interesting. He writes, I was trying to book a doctor's appointment, and the form was broken, so I spoofed it via curl and actually was able to book. Now, you might ask yourself, why was that form broken? Was that office meant to be closed that day? Were they actually no longer accepting a particular type of insurance? But just because your UI doesn't make functionality accessible doesn't mean users are not going to be able to get around it and call the endpoints that are still public-facing and accessible. So things are kind of shifting increasingly to the more severe side. Okay. Now, we're going to take a quick second, put on our black hats, and kind of walk through the 1, 2, 3s of how someone might go about identifying and exploiting these types of vulnerabilities. The first step is you just log into the product. If it's a web product, you can kind of go to your developer tools, open up the network tab, and the first step is just to start cataloging all of the network requests that are happening between your client and the server as you're interacting with the product, as you're kind of moving around different elements of the product. You might look for different sensitive elements of the product. For example, you might go to the account page and see what are the different calls that get made when you try to change your password or when you try to change your security questions. You might go and look for, if you're in a banking app, you might go and look for where your balance is reported, and effectively just try to catalog as many of these network calls as possible. Next step is to actually read through those logs, and you can do regex searches. You can kind of like try to parse them to identify which of these endpoints are actually returning sensitive or important information or performing actions that are interesting. Once you have kind of your subset of endpoints that are most valuable to you, the next step is you kind of just replay them. You take whatever was that network request before modifying any of the payload, and you just see, can I resubmit this request and get a valid response back? And you can do that, if you're in the developer tools, right click, copy as a curl command, dump it into your terminal, and see what the response is. If you get a valid response, that's a great starting point. You can then start to modify the payload and see if you're still able to get a valid response. You can take away the authorization token and see, is there an authorization check at all? Sometimes you can actually just change the characters of the authorization token. You'll find that authorization is actually just looking for a character pattern rather than actually validating that the authorization token itself is real. You can start to look for parameters that might be worth editing, like the object identifiers, the user IDs, claim IDs, things like that, and look for the function semantics and see, okay, this is calling a payload with a parameter set that has do function true. Okay, maybe I can set this other do function 2 to true and see if it will perform this other function as well. Once you kind of have those educated guesses, you kind of just play a bunch of those requests out and see which of them return a valid response. As soon as you hit a valid response, you know you found a vulnerability. Now, this process is very manual and tends to be quite taxing. So you're reading through a lot of these logs. You're doing a lot of command find, control find, whatever, to find specific strings of information that are valuable. And you're using a lot of semantic context to be able to prioritize and understand how to manipulate these call payloads. and each API is going to look different from the next. It's very difficult to sort of programmatically write a script that can, agnostic to the product, do this process for you. But that's all changing now because LLMs are actually very good at this type of task. What you can do is take a valid call payload and have an LLM generate for you a bunch of different options for what could be alternative payloads that you can submit. You can take the semantic construction of the call. So, you have an endpoint called get schedule list in this example. Well, maybe you might guess a bunch of different alternative endpoints like get patient list, get location list, get insurer list, and see if any of those endpoints are able to return a valid response as well. And very quickly, you might identify endpoints that are not in the client or public facing or not meant to be accessible to your particular user profile that are actually responding with valid responses. You can similarly also start to use the LLM to kind of guess for you what are the parameters that I might change and how might I change them. Instead of taking a user ID that is an incrementing integer and replacing it with a hash as your guess, an LLM will kind of give you another type of integer that is close in format or shape to what was in the valid request. And effectively, you can generate a ton of these different options and begin to fuzz these APIs in a way to see which of them will respond with a valid response. This process can then very quickly turn into a programmatic opportunity for you. You can effectively just go through these products and log a bunch of different network calls and have the LLM prioritize and create these guesses for you and hammer kind of these API endpoints for vulnerabilities. And what makes this kind of a difficult attack surface to protect against is you're not just going to be dealing with malicious actors who are trying to exploit your product for their gain at your expense. There are also good actors who are trying to integrate with your product as a way to sort of build a better bridge between your product and their product. A really good example of a legacy version of this is found in a company called Plaid. Plaid is a fintech tool that was the original developer of kind of APIs that allowed fintech developers to access thousands of different banks' interfaces. So if you wanted to be able to pull the checking account balance for a user who had an account with a bank, a small community bank somewhere in the United States, it was very difficult because those small community banks didn't have their own APIs. There was no integration format. And Plaid effectively created these scripts that would screen scrape using valid credentials of a user what the different elements were that were valid. So they kind of created this interface that you could call an Plaid API endpoint. They would execute a script, log in as the specific user with the credential, and go and pull, for example, the checking account balance. They manually wrote all of those scripts. Every time a UI element changed on the bank website, they would have to go back and repair the script. And it took them years to build that initial foundation. Eventually, they built enough market share to actually negotiate real integrations with these banks. But it kind of gives you a sense of the power you have if you're able to sort of integrate with products that don't have, either from a resourcing perspective or interest, a backend SDK that you can integrate with directly. Now, on the right-hand side are a whole host of different modern startups that are trying to programmatically integrate in the same way that Plaid did for just banks with all web-based products, using agents that kind of follow a similar format of finding these public-facing endpoints, front-end endpoints, and interacting with them as authenticated users. They're interacting with APIs that, again, are not meant to be used programmatically, and that's kind of the open surface for vulnerabilities. What's interesting is some of these are foundation model companies like OpenAI and Adapt, and one of them, the browser company, is actually the creator of Arc, which is the vulnerable web browser. Just going to show that just because you yourself are aware that you can integrate with front-end APIs and people can programmatically interact with your front-end APIs does not mean that you're well protected yourself. Okay. Finally, just really briefly touching on mitigations. This is a really difficult problem to solve consistently across your product. And I think if you really want a quick solution, the best answer is to just shut it down. But if you're more patient, you can start by monitoring. Monitoring really means beginning to have a more concrete sense of how individuals might be programmatically interacting with APIs that are not meant to be called outside of the context of your front-end UI. So you might look for session tokens or cookies that are being used in very high volumes. You might also look for a lot of failed calls. Typically, these vulnerabilities are found by hammering the APIs with a lot of different parameters that are invalid. And as a result, you get server errors. And so if you see a user who is generating a lot of failures across your endpoints, it might look kind of benign at the macro level, but obviously that is a very good sign that someone's trying to identify one of these types of vulnerabilities within your product. It'll also give you a sense of which endpoints might be of most interest to malicious actors that you can prioritize for mitigation. Next step is to build some sort of harness for you to actually test before your products roll out these types of public API endpoints. Ideally, something within your CI/CD process where you have a test harness that can identify different parameters, different authorization logic to test against these endpoints to make sure that as they're being rolled out, they're returning valid and invalid responses when appropriate. You ideally want to have something that looks like a fuzzing interface, similar to what an LLM, powered interface that we talked about earlier might look like, because that's kind of what a malicious actor would be using to cover the broadest scope of potential vulnerabilities. But it can be as simple as a couple of different unit tests as well that you write in the process of your CI/CD process for each endpoint. And then the last piece is just beginning to refactor your product wherever there are vulnerabilities or potential vulnerabilities. One of the most important things is if you have a product that still is using guessable IDs, particularly incrementing integers, especially global incrementing integers, you got to change that. Wherever you have the opportunity to make your front-end APIs that are not meant to be used by programmers less legible, less semantically obvious, there's an opportunity to create obfuscation and make it harder for these types of actors to identify and exploit your product. So with that, I'm happy to pause here. If anyone's interested in these types of vulnerabilities or finding mitigations for them, would love to chat with you. And if you have any questions, here for another couple of minutes.